I think we are ready to go. Hope everybody had a good weekend. So nobody in here is from Pennsylvania or Philadelphia, but anybody from there? One, are you?
Not me. I know my friend I work with.
Okay, he's watching later, so congratulations, all those from Boston. Sorry. Was there one of you at least? Yeah, you've won a lot, so, it's not like, it's like, oh, it's already had like a big piece of pie, and like you just wanted one more piece. It's all right. Philadelphia gets to celebrate. All right. So we're going to continue on dynamic mode decomposition. Remember what we were talking about last time? And the DMD method. And by the way, my other class, who made the comment about they were born in the 90s? Like, they're even younger than you guys. And they all knew AC/DC. Just bringing that up because I was a little ashamed on your behalf. Okay, anyway. All right. So anyway, maybe I'll put that on a homework, like, go through the, I'll give it in ranked order of my favorites. Okay. AC/DC songs. All right. So we're going to do DMD, and remember what we were trying to do is say I have a system that is evolving in time. It maybe has some parametric dependency. And remember, part of the argument here is that when you measure systems, there's a lot of systems you actually can write down the equations for. But more and more, there's a lot of equations you can't. You don't know what F is. You can make something up that you think might work, but one of the things we're heading into these days is the fact that if you're working on fairly complex physics problems, multi-scale physics, biology, you don't have a good model often for F. Okay? However, you would like to be able to build a model, make reasonable predictions into the future, look at the patterns that are there, and specifically dynamic patterns. And so the DMD, as I showed you last time, was just basically, I'm going to approximate this with the best fit linear dynamical system. Okay? And the hope is that X at least somewhat replicates what's going on with Y. Okay? Clearly, this is linear and that's nonlinear, so obviously we're missing some things. However, if you sample over time frame, some snapshots of time, the hope is to build the best model. And the interesting thing, again, I want to highlight is you're not committed to an A, right? It's the current A that best represents the system over the time you sampled, but you can keep just updating this model as you go. Okay, just take more data in, build a new matrix A, take more data in, build a new matrix A. So you're building on the fly the best linear fit model, and you can just keep updating it. Is that good? So that's kind of a nice, flexible method. Okay, you need flexibility in most of your methods if you're going to really do interesting things. Okay, the advantages, again, if that's linear, I can solve it. It has a solution which is equal to the sum b of j, phi of j. And we're going to do a rank arc truncation. So there's this idea that there's some modes and eigenvalues associated with the dynamics, and then I can represent the solution like this, and allows me to do future state prediction. I can put any time I want in there, including a time in the future. And so I can get a prediction from this model very easily by doing this, whereas the only way to get, I can't even get a prediction for the future for this model because I don't know what F is. It's not like I can simulate the future. All I have is data, okay? Everybody go with that? So that's the idea of DMD, yeah? Here? Yeah. Or if you went to University of Indiana, I'm promoting your school. Have you seen IU? No? You guys seen IU? Yeah, okay. If you're from Midwest and you've been in the Big Ten, you know that it's something like that. But IU? Okay. All right. We used to play them in Ultimate Frisbee back when I was in grad school because I was in the Midwest. They were in a really, Indiana. We were in Chicago at the Northwestern, so it was like awesome, and then everybody else was in like a cow town. So, easy to make fun of. All right, so this is going to be our thing. And the last thing I want to point out, so we are going to do rank truncation, and importantly, unlike PCA, this associates every mode with the time dynamics. This is really critical, actually. This is what kind of makes DMD actually worthwhile to consider as a technique for your data. PCA does not do that. DMD does. The implications are they can be big, depending on the problem you have. Okay, so let's go program some of this up. That is just the shell of a reminder, what we have. Then we will go to coding and showing how this works. All right. So let me bring this back up. So I just want to, again, point out to you that many data analytic tools are kind of originally defined as just an algorithm. And that's the same thing with DMD. It's just an algorithm. And in fact, if you look back at the clustering and classification lectures, there's many of those clustering and classification schemes are just defined as an algorithm. Okay? Whether you do k-means or some of these other things, sometimes people then will later write it as an optimization problem, which typically they are, but normally people just did it. They defined some algorithm, and it kind of works, and it's like awesome, and we'll justify it later. Okay? Same thing with DMD. It made sense. People used it. We go from there. Okay, so what I'm going to do is I'm going to make, you've already seen this. We've done this before when we were looking at independent component analysis. So I'm going to make up a space variable. These are, these are out of the notes I sent you. So it's a spatial temporal decomposition. So I'm going to make an X domain, and I'm going to make a time domain. So I have 400 spatial points, 200 time points. Okay? So I've made up this domain here, my dt between steps. So that's my dt. That's my, essentially what my measurement clock is set to at this point. Right now we're going to consider evenly spaced sampling in time, which is often the case, but you can generalize the DMD to handle arbitrary time stepping or sample points. Okay, X grid T, I'm going to teach it that it's a space. Boom. So the mesh grid now builds an X direction and a T direction. So now what I have is my shell, my structure on which I'm going to build some functions, and I'm going to try to decompose them. Okay? All right. So what I'm going to do is create two spatial temporal patterns. Okay, so here's going to be the objective of the code. What we're going to do is we're going to take two space-time things that are doing something in space-time. We're going to merge them and just observe all of it at once. And our goal is to try to pull them back apart. Do you remember in ICA we did this, right? We just said if I'm measuring two mixed signals, how do I pull them back apart, right? You don't have the luxury of knowing, oh, there's this one and there's this other. That's the whole point, is you're trying to figure out if there is one and another, or what's going on with that. So this is going to allow us to sort of just merge them. We're going to look at it and say, like, okay, what we know is our task is to just take the measured data, which has two signals together, and to try to extract them and separate them. Okay? This is what you would do in a practical problem. Okay? You get them mixed. You want them unmixed. Okay? All right. So here we go. Let's make signal 1, F1. We'll show what these are. Okay, two signals. And so we're going to do, and by the way, the combo is just simply, all right? So let's plot some of these things. So these have imaginary values, so there's a phase winding on these. It's e to the I 2.32, so it's winding around with omega. So essentially what I try to do is this, if you could see behind here, right, I wrote down the solution is in the form, shoot, let me just write it again. If I had planned this better, I would have written it down here instead. Remember that my solution is in the form, and really that's kind of what I'm doing here, is I'm imposing two different signals, two different phis. So I'm kind of actually putting it in this form to begin with, adding it, and now just saying, could it actually back it back out? Okay? Everybody go with that? So that's what I did. Omega for one of them is 2.3, for the other is 2.8. Phi of j here is the mode that I have. Okay, so let's plot some of these modes and some of the structure. So subplot 2, 1, 2, 2, 1. Absolute value. Actually, I will plot the real part. Surf L real X grid T real F1. And we'll do the same thing. So let's just plot the raw signals together and then mix them, and then we'll build our DMD algorithm.
Pardon, Professor.
Yep.
There's an I missing in grid on F1.
F1 in grid. There, yes. Nice. The voice of God has come. You are paying attention. That's awesome. Mostly everybody's just there and down there is paying attention to see what I'll say. Not my code. But this is great. Thank you for catching that.
I like code.
All right. All right, that's a little bit, let's do some shading and terp on that. And some color map. Gray. So this kind of like gives a nice lit surface. All right, there we go. All right, here's my two signals. Okay? So there's one of them. There's the other. So they're kind of simple functions. One's a sech, hyperbolic secant. One's a sech tanh. Okay? So all I did is I just made up some things. One of them is sort of here's 0, let's say. Remember I shifted one over like that. It's like the sech. The other one is a sech tanh, so it's, oh, sorry, like this. So those are my two functions I should be thinking about getting out of this thing. That's how I built this. Those are the two modes here. And oscillating, okay? So one's faster than the other. And what we're going to do is take a look at what would PCA give us and what would DMD give us, okay? That's going to be our goal, so we can compare and contrast these two methods. All right, so there we go. And then the mix, of course, is going to be in subplot 2, 3, 2, 2, 3, which is F. That's our mix. Okay? So now you can see this thing mixed together, and that's this bottom plot here, and this is what you measure. Okay? So the question is, if you measured that, could you back out those two functions that made it? All right? The assumption here, so first of all, let's talk about the impossibility of this problem. Right? The impossibility of this problem is the following. I have a grid of measurements, which is 200 by 400. Okay, so I give you those number of measurements. And I'm asking you to construct two matrices that are 200 by 400. Right? So how can you do this? We keep doing the impossible in this class, right? I say, like, you can't solve this. This is massively underdetermined. I give you 10 variables, and I'm telling you, give me 20 back. What's the assumption? The assumption is that you have distinct time signals. So remember, whenever you have what looks like an impossible problem, usually there's going to be a constraint involved in solving it. Okay? That's just generic principle. Okay? You either have no solutions, infinite number of solutions, put a constraint, boom. Sometimes these constraints are called regularizers. So you'll hear that dropped in conversations. Oh, you do this and some regularization on an optimization. All the regularization is doing is adding you a constraint so that you can actually solve the thing. Okay? Just keep that in mind. That's what we're going to do here. Our constraint is that this thing here has distinct time dynamics. Okay, so the first thing I want to do with this signal that's mixed is SVD it. So that's going to give us the low rank structure. So let's make a figure and see if it actually does come out to be low rank. So plot the diag of S divided by the sum over the diag. Sum of the diag of S. Okay? And with a big red dot. And let's just take a look at what we get here. Oop. I am missing a parentheses right there. Thank you. Okay. So here's the singular value decomposition. 200 modes. And notice what happens. There's two modes. One up here, two there. Awesome. So essentially, the first one has about almost 60% of the variance. The second one has about 40%. Pretty much they're eating up about all the variance. So this is a low-rank structure we're looking at, which is going to be generically the case for you. So it's great. So I can actually start already thinking about a rank 2 truncation of this thing. So what I'm going to do with this is take a look at what this gives me in terms of the time dynamics of the DMD, sorry, the PCA. So if we do PCA, we can look at two things. We can plot, for instance, the first two columns. Actually, let's plot 3, just so you see that the third one is meaningless, and plot its time dynamics. Okay? So now what we have here is we're going to plot essentially the left and right singular vectors of the SVD, and it's going to tell us what the spatial and temporal things look like. Oh, maybe let's do this with the real part. So it was trying to actually plot on some imaginary axis. Remember, we put imaginary numbers in here, which is fine. SVD. Does SVD always work? Good, thank you. All right. Thanks for shaking your head. Always. I don't care if it has complex numbers or not. All right, there we go. So, hold on. Oh, you know what I wanted to do? Let's do that. I wanted to transpose it. There we go. Okay. So I want the U to be spatial, but the way I was stacking it was wrong. All right, so first of all, you start looking at this thing, you see right away, first two modes look good. This yellow one, which is the third mode, is actually just junk, just from numerical round off. So you can clearly see it. This is not a mode. It is not something physically interpretable. It is just simply, unless you want to try to interpret round off in your computer. There's nothing there. So let's get rid of it. Everybody good with that? So then this is always a good sanity check for you. For when you're going to truncate, you can look at the mode you're leaving out, and you can clearly see no love lost there, leaving that guy out. Okay, there we go. Now here are the modes. So let's interpret these for a minute. Here are the modes on the top. Here's what they're doing in time. Now what they should be doing in time is exactly oscillating, like cosines, right? One with one frequency and the other. And you can see that it's not. I mean, they're oscillating, but they have some like beating going on with them, right? So when it did this decomposition, essentially it mixed those two signals, the SVD did, and said, oh, well, I'll give you two modes, just that I'm not going to really pay that much attention to how I decompose in time. So it just mixes the two signals. So here are your two modes. That's what they look like. What should they look like? Here. So mode 1 should just be a hyperbolic secant. Mode 2 should be sechtant, so it's like a little up-down thing like this. This is what it should be. This is the truth, the ground truth. Okay? And what it did is said, well, since I don't have to respect this thing, SVD is just looking for correlation. It says, I gave you two modes. I already did my job. Okay? So I'm going to give you two modes, except that I can mix them together. And when you mix them together, it produces those two modes instead. Okay? All right. So that forms a basis, which you could expand things in. But it's not the basis you want, in the sense that it's not as interpretable as if I can actually maybe extract this thing where I get back to the original modes that I had in the system. So this kind of reflects a philosophy that's going on here. Philosophy is the following, which is when you have a lot of signals that are combined together, that many of them have their own distinct frequencies and signatures, and you are respecting that, and you're saying, you know, stuff that's oscillating at this many hertz should be grouped with other things at that many hertz. Maybe they're part of the same signal. Things that are, 50 hertz should be grouped with 50 hertz things. Things that are 0.1 hertz should be grouped with 0.1 hertz things. So it reflects a philosophy. Is that the right thing to do? When you look at data, you don't know if that's the right thing to do. I'm just making that up. But somehow we have this idea that things that generate, the physics that generates 50 hertz probably should be clumped together, right? So it's sort of this bias we have that whatever's generating that, let's put it together. Whatever's generating the other frequency is distinct, and we'll put those together. Does that mean we're right? It's a bias you're going to take. It's a bias I'm going to suggest you take in a lot of problems. Okay? It gives you a lot of nice physical interpretability about signals from measurement data that are mixed together. Okay? All right. So remember when we set a constraint here? I'm solving the impossible problem. One way to think about what I called the constraint or the regularizer, it's simply you putting a bias into your problem. When we were solving the compressive sensing problem, I say, hey, it's big AX equal to B. My bias is I want a solution that promotes sparsity. So I'm going to go ahead and penalize with an L1 norm to make most of the stuff 0. And in the cases we were looking at, they made a lot of sense. But that was my bias I brought in, right? That was how I was going to solve the problem. This is no different. Just like I believed in compressive sensing, only a few things should be non-zero, I'm going to say I believe there's distinct frequencies and modes. That's my bias, and I can impose that bias, and we could call it a constraint or a regularizer, whatever you want to call it, but you can think about it as a bias. Okay? How you want to solve the problem. All right. So this is the results here if we do not impose anything. We just say, I don't just look for correlated structure, give me something back, and that's what that will do. All right. Time for DMD. All right, so first of all, let's see. I want to make some, yeah, okay, that's fine. All right. There. I can type right. So let's talk about the DMD algorithm that we want to actually create here. And what I'm going to do is make a data matrix X. And it's going to be this data. I'm going to go ahead and transpose it so that the rows are spatial measurements and columns are time snapshots. Okay? The way I created the F was different. Time was rows, space was columns, but now I just flip it around. So remember the DMD algorithm breaks this matrix up into two pieces, right? The first piece, X1, is going to be the first set of 1 to n minus 1 columns. X2 is going to be x second to end. Okay? Yes?
Is your data usually, for DMD analysis, do you usually structure or shape data so that way your timestamps are within like the columns? And then
I usually do, yeah. So a lot of times the way that DMD is presented is columns or snapshots in time. Because what it's going to do is, okay, good question. So how you shape your data is up to you. But in this case, or in most cases, people put columns as time, because what you're trying to do is a regression to here. And the regression to here, this is the interpretation, this is a time variable. That's the column space. So if the column space is time, it's going to give you this as time. And if you've done it the other way, it's going to try to fit Fourier mode spatially, e to the I omega x's, which is a very different problem here. It's not clear how low rank it is, and right? Because now you're trying to represent this now as exponents versus the time, which is clearly 2 exponents in the data. Okay? Yeah, actually, it's always interesting when you have data. You always want to kind of back out a little bit of what do you want to do with column and row space. Because in some sense, with the SVD, all it does is it just flips your interpretation of U and V. Who cares, maybe? But when you come to DMD, it kind of does matter. Like, well, geez, because you're mostly saying, once I find the U space, I'm going to project into it. So now you can't just say, well, U and V, who cares? I can just take care of it later. Right up front in the DMD method, we're going to do a reduction, and then we're going to, remember, we're going to go pop ourselves into the low-rank subspace of U. So if you switch the interpretations of U and V, you're now building a low-rank model in the time space versus the spatial modes. Okay, so there we go. And remember, that's like step 1, and now we're going to go ahead and rank truncate this thing. So the algorithm, we're going to do a 2-rank truncation. So we're going to say U S V is equal to SVD of x1 econ. So this is a step 1 of the DMD algorithm. Do the SVD. Okay? And we went through the algorithm in class on Friday, and that was the first step. There was basically 4 or 5 steps to put this all together. Step 1 of it. And what I'm going to do now is, that's the econ. I'm going to say U of R is pull out the first R columns. In this case, 2. It's going to be a rank 2 system, so all I care about is the first 2 columns. So right away I do the SVD. I find the low-dimensional subspace, which is U of R. So the U of R is the rank-reduced U. Okay? S of R is equal to S1R. Oop. Okay? Now I pull out the 2 by 2 matrix, defining how big they are, and then also the first 2 columns. And we can play around with the rank R as we want, right? So generically, you can always decide, hey, I want more rank, less rank. Very few problems are going to come out as nice as this, right? Where it's like exactly 2 modes. Most of your data is going to have this big, long tail that goes off into the sunset. And at some point, you're going to say, I got to cut this off. So for instance, in your eigenfaces, right, you had to make some rank truncation decisions around that, right? It just kind of keeps tailing off forever. So you say, like, I don't know, I'll take 100 eigenfaces, or 50, or 200. Whatever you do here, this gives you a subspace that you're going to work on. Okay? All right. Now remember, once we got down to this space, we could actually then just simply start building the A tilde matrix. And I'm not going to go back through and write it up on the board, but here it is. This is what it came out to be. That's what I wrote down. And this is essentially a similarity transform with A. So it's in the, you're going to build this matrix A, which takes you from one snapshot, set of snapshots to another, which is the least square fit matrix. But you're now doing it in the low rank subspace. Okay, so that's A tilde. Let me make sure I got it right. Yep, okay. Once I have that, then you just do eigen decomposition of that matrix. That's going to give you, this is, it's going to basically give you your eigenfunctions and eigenvalues. Okay? And if you want to get back to real space, these are going to be the DMD modes. It's x2 times VR. There it is. So phi can't contain my DMD modes. Kind of as simple as this. SVD, look in the similarity transform variable there. Eigenvalues, project back out to real space. Now the eigenvalues, the lambdas, or so of this are the diagonals of D. And the omegas, which is, so this is what's called in the Poincare space. So if you want the e to the omega t, that's what lambda is. So to get to the omega, then you've got to basically say take the log of the data divided by dt. Okay. So there we go. I have now my eigenvalues in DMD modes, DMD eigenvalues, and we're ready to go. Okay? So now that's the decomposition, and we can actually start to look at what these modes look like. So let's go ahead and pop those up. So what I'm going to do here is on figure 3. And what we're going to do here is plot phi's. Let's see if this actually does an okay job. Do I do a subplot? I do need a subplot. Okay. All right. So what happened? Hold on. Oh, I need it here. So hopefully you all saw that awesome result. Essentially, all right, so let's interpret this and let's make these line widths. You guys can't see that so well, I think, as well as I can, at least up on my screen. So we'll do a put that also on the other one. So here's the money, right here, this plot. Okay. What I want you to compare is the blue and the red are what you get from SVD. So the red is this triple bump thing. The blue is this a little bit wonky, which are not the right modes. The DMD modes are purple and gold. Husky colors. Why didn't you know that? Okay, there we go. So they go. One of them was supposed to be hyperbolic secant. The other one is supposed to be sec-tangent. Totally pulls them out. What I got back was exactly what I was hoping to get in like the ideal world, which is exactly the two signals that I put in. I measured them jointly, and this thing said, I'm going to separate them from you, subject to the fact I want all the time dynamics separated. That was my subject to line or my constraint that I put in. And what do you get? Exactly these. Essentially, you decomposed it correctly. Okay? So this is kind of awesome. So I have now great modes. So what I just did, or at least showed you, is Remember, it's all back down to this formula here. This is the solution to a linear differential equation. And it has some modes and some eigenvalues. And I actually put in a mode and an eigenvalue, and I actually got exactly back the right mode. Okay? So it's great. It's fantastic. Now we can go and say, well, did I get the right time dynamics? So what we're going to do is try to reconstruct all this. And you'll see, how does my reconstruction look in this versus what the thing was in the first place? So that's what we want to look at. Everybody go with that? So that's so it's one piece of good news so far, is that. And by the way, when you plot the solutions, what's their they are exactly oscillatory now. So even if I were to show you here, right, where it's oscillatory with some envelope, the DMD gives you perfectly oscillatory time dynamics. Remember, it's a regression. One way to think about the regression it's doing is saying, find me the mode so that this thing here is exactly oscillatory. That's another way to think about the constraint. It doesn't have the potential of modulating in time. It just simply says, no, you have to be a pure tone. Okay? So it's a constraint on how I find you solutions, and in that constraint you get back exactly what you were hoping for. Okay, so let's reconstruct the solution and see how we're doing. Exciting stuff, yeah? Okay, I'm excited about it because so far everything's working in the code. And so here's what we're going to do. We're going to go back to here. And we're going to say, okay, remember, here's our signal. Here's our two modes. And actually, I could replot. I got the right modes out. And the question is, does my DMD model reconstruct what I see here with those two modes? Right? So that's the sanity check we have to do still. So let's go ahead and do a reconstruction in time. Okay. One last thing. The initial condition for this is called x1. It's the first column of x. Remember, I started taking samples in time. X has, all the time snapshots. So what x1 is the first column. So at time 0. Which means the b vector is phi backslash x1. Let's talk about how I got that. So remember here, I have this as my solution. At time t equals 0, e to the 0 is 1. So this thing here can be thought of as essentially all my modes times some vector b is equal to the initial condition, ax equal to b. And at this point, what we're going to do is just do the standard MATLAB thing with the backslash to get the b. This tells you essentially how much of each mode is going on. At time 0, here's your thing, project it to there. Hey, by the way, why not project this on some other time? You could, right? How about time 1 or time 2? You could put in a different time here. And actually, this is actually really kind of an important thing for DMD, is how do you regress to that variable b? Turns out DMD, straight up, exact DMD like here, I'm presenting to you, is not that good, especially if you have noisy data. But you can optimize. Again, it's always an optimization problem, right? So if you haven't figured out, this whole class is always coming down to some optimization, some constraint problem. That's all data analysis ever is. So if you can just get that in your head, say, I'm going to do some data analysis. What you're really saying is, I'm going to do some optimization with some priors and constraints that I made up to try to get something I want out. Okay? That's what we're doing here. I won't talk about that much, except the optimized DMD does an amazing job with that one. Gives you the best B's possible, and the best omegas, and the best modes. Okay? It's actually structured as a much better optimization problem than this pseudo-inverse regression. So that's what I just did here. So now I have B, this, and this. So now I can just construct everything because everything's known. Okay? So let's go build some solutions and plot them. Okay, so I got that. So what I'm going to do is build some time dynamics. So here's going to be my filling up a matrix that's of rank, has R rows, T columns, because I've got a two-mode expansion. What I'm going to do is build the solution iteratively for each time. So what I did here, for each one in time, I'm going to compute this here, this times this. B times e to the I omega t. So as t changes, I keep updating this value. For each updated value, I make essentially now, I make a matrix of this, and then I'm going to multiply it times this thing here. Okay? To make a full matrix. Remember, I'm making an outer product. I have two modes of rank R that are long like this, so it's two columns. And then here's what they're doing in time. And so I'm going to put them back together so that I get a matrix like this. Okay? Time, space, multiply it out. Space, time, just like I started. Okay? So I just built this vector here, which is the time matrix. And now, my DMD solution, here it is, phi times time dynamics, done. And then I can subplot this, subplot 2, 2, 4. And I'll do, let me just pop all these nice commands over here. And x, so real part x DMD. Is that what I called it? Yes. Okay. And run. Oops. I'll have to go back to the figure. So first of all, I think I have real. No? What's going on here? Oh, I might not have this. So 400 rows, yeah. That's correct, yeah. All right. Oh, yeah, it's correct. Okay, so fine. Yep. So I would come here and do that. All right. A little hacky, but that's all right. We'll just hack it up. And this should be figure 1. Okay, so we're going to go back to do this in figure 1. Let's see if that's, thanks. There we go. Boom. Compare. Nailed it. This is a rank 2 approximation to the dynamics. What it did for me is several things. One, pulled out two modes. They were exactly the two modes. It pulled out their dynamics, their time dynamic, the oscillatory frequency. The time dynamics are fixed. They're sinusoidal. So all it was trying to do is regress to a frequency and a mode to go with the frequency. Very different than PCA. PCA is trying to say, let me give you a combo of U's and V's to embed this in, so the V doesn't have to take any, it's unconstrained, the form it takes. DMD says, no. Oscillation frequency and a mode with it. And the important thing here is, remember, I set the DMD back to here. All this, so I built the modes and the frequencies. I projected on two-mode projection, just set up on the initial data. All that is future state. I'm not like keep fitting it to the data in the future. So I've run it all the way to time, whatever, 15, 20 here, into the future, all based upon at time 0. Okay? So that's a pretty nice result that we have here. One other thing I want to show you is you could say, awesome, so I can do future state prediction. Because you can. So I could go further in time. So if I go further in time, that's going to screw this up. Let's just make sure I do this, then I can run it for any time I want to the future. I think that will work. Good. Now, okay, good. So I took away the actual time, and let's go. Let's double our time. This is going to go through omega time dynamics, 0 is r, okay, t iter, oh. How about this? So what did I change here? Okay, so here's what we're going to do. I'm going to go to the future. T2 is going to go into the future. Remember, T was this here. Now we're going to make T2. I don't know. We'll go twice as long into the future. Everybody good with that? And that's T2 now. I think we got all the T2s right. So now I'm going to go, I was going out before at the time 4 pi. Here's it at 8 pi. I just predicted the future. Okay, so of course you're not that impressed, right? You guys are just sitting there going like, I'm not having a big deal. Okay, but that's essentially what I did. I don't have a model. So remember, this is what's, I think, important about this. Come back to here. I don't have a model for getting me to the future in time. I sampled from 0 to 4 pi. I built a model, and notice what I did here. I said, okay, I'm going to estimate what this thing's going to look like in the future, all the way to 8 pi. So I've doubled the time, and there it is in the bottom. Okay, awesome. When does this break down? Well, let me show you something. I think almost see it there. Let's go out a little further. 20 pi. Ooh, not bad. Still working. 100 pi. Actually, this might be okay. So I can predict quite a ways out into the future with this method. Now, what's the danger? The danger in the DMD is, you see these eigenvalues here? If just one of them has a slightly real part, what's going to happen to my solution in the future? It's e to the blah, positive. There's only one thing this ever does. It goes to infinity. Okay? So what it's going to give you is a finite horizon. What's kind of amazing about this, how well this is working, is, and it's partly because it's a very simple problem. Generically, when you do the regression, most of your eigenvalues should be right here on the imaginary axis. If they're a little bit over on that side, your solution, what? Blows up. If they're a little bit on this side, your solution does what? Goes to 0. This one, remarkably enough, seems to be pretty much dead on, because even after 100 units, it seems to be oscillating. So that means and of course, this is a very simple example. So what happened here is it actually gave me eigenvalues. We can actually look at them. Should we look at them, the eigenvalues? They're the omegas. Here we're going to do omega. Format long E. Omega. What? Yeah. Okay. Check it out. The reason we're doing so well is, what's the real part? Numerical round off. So in this case, okay, so don't be deceived. Okay, so right, I showed you how it works. Awesome. I could go and brag about it, blah, blah, blah. But this doesn't usually happen. There's a couple of things that usually don't happen. First of all, you don't get exactly 2 modes, right? So there's a tail, and you got to truncate. Second, your eigenvalues are almost never real parts that small. Usually, oh, there's an eigenvalue at 0.01. But that's okay. Again, all you're looking for here, short time future state prediction. And this gives you a model on the fly, even if you have no idea what your model actually is. And you can just keep updating it. Take more data in, keep going. Okay? There's your dynamic mode decomposition. Yeah?
If your system you expect to be like aperiodic or chaotic, can you just like tighten up the window?
Yeah, so if you have dynamics that's kind of changing around, then what you can do is change your sampling window, make it short enough so that you can get a good model. And then, of course, if you're on an attractor and it jumps to another, the model will be good here. Right in that interval when it jumps, you're probably going to have a very bad model, but then you're going to get a good model again. All right, enjoy your Monday.